Electrochemistry. This is the first part that will be on the next exam. So, the electrochemical cells, definitions, and applications. Now, let me warn you in advance, the trick to electrochemistry is keeping your definitions correct and straight in your head. So, electrochemical cells, the energy is released through the electron movement. And so, if we tap into this movement, we can use the electric current that's associated with it. Now, by definition, if a cell is spontaneous, that means it'll run on its own. You put the right two half cells together, more about that in a little bit, then you're going to get spontaneous electron transfer. These are voltaic and galvanic cells. From the Italians, Galvani and Volta, who spent a lot of time playing with frogs and messing with the nerve cells and seeing how electrical impulses make the nerve cells. And the interesting trivia piece about the electrochemistry is this is where Mary Shelley's Frankenstein came from, because they were playing with electricity and trying to reanimate the dead. Hence, that's where all the bells tied to a dead person's hand, in case they were not dead, they could pull the bell and people could hear. It's kind of interesting, but believe it or not, it's all based in the fact that they were playing with electrochemical cells to study nerves, etc. So, because of these two guys, we call spontaneous cells voltaic or galvanic. We will do non-spontaneous cells later. That's electrolytic. You'll also encounter one in the lab. Now, these cells operate on the difference in the potential or the energy electrons that we transferred in the half cells. So we call this the cell potential is the difference between the electrodes of an electrochemical cell. Okay, this is what a voltaic or a galvanic cell looks like. This was one of the first cells. This is called a Daniell cell. And what you're doing is you're moving zinc, attaching a zinc cell to a copper cell. This you're going to find out is the anode, and this is the cathode. They're labeled. And if you'll notice, the electrons are flowing this way. So, and you have what's called a salt bridge that allows the ions to migrate, because if a charge builds up, positive or negative, in one side, then the reaction stops. Think of a circuit. If you've ever played with circuits and you light a light or something by opening and closing a switch, the circuit must stay completed. Okay, so in order to compare apples to apples, we've got to get our same terminology going. So let's talk about the parts of the cell. Okay, first off, the anode is the electrode where oxidation occurs. And that means that electrons are released. If electrons are released, we end up with a positive charge. The cathode, on the other hand, is where the reduction occurs. The electrons are gained, so you have a positive charge. Now, there are all kinds of mnemonics. There are all kinds of things that you can do to determine what's what. But for me, there's an O in anode, so it's oxidation. And cathodes start with a C, as does positive. Okay. And there's an N for negative. That's what works for me. You can make up your own mnemonic. You can figure out whatever way you want. Biggest thing is you've got to remember these. Now, the anode and the cathode are connected by a salt bridge or fret. Okay, this is to complete the circuit. This allows the ion movement between the cells. Now, the difference between a salt bridge and a frit is a salt bridge is what we saw previously, where you have a tube with the salt in it, bridging over. A frit is more like a ceramic disc, like a clay pot, where the water can come out. And here's the fun part. The electrode is either the solid or the half cell. So you can refer to it as connecting two half cells or two electrodes. And if you've got a solid metal that can be used to transfer the energy, the electrons through the system, that's also the electrode. So I didn't make up this terminology. So this is figures from different texts. This one uses a frit, which means it's permeable to the ions. Permeable to ions. Okay. But basically the two half cells are still separate. Here is your salt bridge, which bridges, and these look like little rubber pieces, but remember, these are going to have to let the ions flow in and out as well. Okay. So, if you're dealing with two electrodes, one of which involves a gas, then if you'll notice, I have no earthly idea why I always want to put an S on gas, E on gas, is that notice you're going to have the gas coming in and bubbling. That's where all the bubbles are. And this is either usually your gold, platinum, palladium, several other things. These are usually a non-reactive metal. They will still react, but they have a really high potential. This particular one is what's called a standard hydrogen electrode, or an SHE. You don't say she, you say it's an SHE. Okay, but again, this is still the cathode. The other one is still an anode. Okay, so if you'll notice, when you write them, the anode is always written first, the cathode is written second. I remember this because it's written in alphabetical order, A, B, C. Okay, so these are actual cells. This is a blow up of the one involving the gas, and again, they're using some inert electrode to do the to allow the electrons to move through the solution. Because if you didn't put an inert electrode in there, then the electrons couldn't flow and the reaction would stop. Okay, these are simple slides of mine that it's easy to label. This is the anode. This is always the cathode. This is your salt bridge. And your anions are coming in here. Your cations are coming back in here. These are acting as counter ions. Now remember, you do have to have the anions going back in and then the cations going back in. Here's your electron flow. This one's positive. This one's negative. Same thing for the frit. If you'll notice, as the metal electrode loses the electrons, it forms the positive ions, and that's why the positives must be counteracted by the negatives. And here you're losing positives, so you have to have positives coming in. You're becoming basically more negative here. So these are basically the simple parts of the cell, and this is the easiest way to draw it. However, this is bulky. So the way to draw a cell in shorthand, without having to draw all the pieces apart, is a shorthand notation. We start by putting the anode and the cathode. Okay, if there's a concentration, if it's not a solid, then there's a concentration. If it's a liquid, you use molarity. If it's a gas, you can use atmospheres. This double parallel line symbol is your salt bridge. If you have a phase change, that means you go from solid to aqueous, or aqueous to solid, or gas to aqueous, whatever. It doesn't matter what the phase change is, then you use a straight line. If they're in the same state in the half cell, you would use a comma. So, for example, if you had iron 2 plus 1 molar with iron 3 plus 1 molar, they would be in the same cell, the same electrode. So they're in the same state, so you would put the comma. An example of this is, remember the Daniell cell, and you can go back and look at it. Remember, this is the anode, the zinc is. We're going from zinc solid, phase change, to the aqueous form. We have our concentration, and then on the cathode side, we're going from the copper ion into the copper solid. Now, if you want to think about it, if you were to run a wire here with the electrons flowing this way, then you would complete the circuit. Okay. Now, remember, in the case of a gas or two liquids, because if you had iron 2 plus and iron 3 plus, there's no solid there. You cannot throw in iron metal because that's a different reaction. You usually use platinum or gold flags. The nickel and other ones can be used depending upon what you're doing. But the bottom line is that the most common two are platinum and gold. So if we have a solution in reaction, and remember we did this reaction at the beginning when we were balancing. And if you'll notice, there's no solid in there. So here we use an inert flag at this end and at this end. Now, if you don't need them, don't use them. Like up here, we have no inert flag because in both cases we have a solid we can attach it to. If you don't, then you use it. If you do, then you don't have to use it. Okay, so we're going to assemble a galvanic cell. We have a simple voltaic cell as assembled. We're using nickel and we're using cadmium. Okay, this is our overall reaction. So the question is what reaction is at the anode, what's at the cathode, etc. Well, nickel's going from 2 plus to 0, and cadmium's going from 0 to 2 plus. So this is a gain of electrons, so this is reduced, which means cadmium is oxidized. Okay, now we've got all that stuff, and basically what it's saying, complete the cell diagram by indicating everything. So what they're really asking us to do is draw a cell. So if we come to another page, we're going to draw, I'm going to start with my 2 half reactions, and I'm going to put in my salt bridge. And again, you don't have to be totally pretty, but we've got on this is the anode. And so if I remember right, our anode is oxidation, so that's going to be our cadmium. Cadmium is going to cadmium 2 plus 2 electrons. Our cathode will be the nickel, so that's nickel 2 plus 2 electrons is nickel solid. Now these are both solids, so when we start, this will be cadmium, and we'll do the same thing over here for nickel. All right, we're going to complete the cell. So what we're saying is the cadmium is going to form cadmium 2 plus here as the electrons flow out and into the nickel. So we have our electron flow. This is going to be positive to attract it. This is negative because it's coming out. Okay, as the cadmium forms more positives, we're going to need anions to come out of our salt bridge. to counteract. And remember, cations are going back in here. On the other side, we've got the nickel 2 plus going to the nickel metal. So actually, with time, the electrode here is going to shrink. And on the other side, your nickel electrode is going to get kind of all fat as it gains fat. Why do I keep putting E's on things? As it adds metal. And that would be how we played out. Okay, just to make it pretty. Oh, I didn't finish. As the nickel goes out, we've got to replace the cations that we lost so that our charge stays neutral. Anions will be going in here as it goes. And just to finish it out and make it pretty, I'll do the liquid levels. So I think I've got everything I'm supposed to. Let's go back and double check. Reaction at the anode we got, cathode we got. They're labeled with the directions of electron flow in the external wire and ion flow in the salt bridge. So basically we answered all of the questions. So this is the cadmium nickel reaction as proposed. Now, you will be asked to do something like this. Not really sure how yet. Still working on that because of the quizzing feature. But you may be asked to draw a diagram. Now, the other trick to this is this has to be a galvanic cell. Galvanic means that E cell, which we haven't gotten to, is greater than 0. So it's positive. Okay, and we'll go into that in the next phase.